Hello everyone, my name is Natanya Rees. Today I'm going to present our work, DreamBooth, fine-tuning text-to-image diffusion models for subject-driven generation. This is work that was done along my collaborators at Google while I was a PhD student at Boston University. Using DreamBooth, one can generate new images of a specific subject, such as this dog, in different contexts and with different semantic modifications, given only a small number of unconstrained input images. Here we have a summary of the method. Given a small set of 3 to 5 input images, we first generate a unique rare identifier for the subject, V in this case, and subsequently fine-tune a pre-trained text-to-image model on the small set of images using the subject's class name and the rare identifier as text supervision. At inference time, we can use sentences such as a V dog in the beach to generate new images of our specified subject in new contexts and with semantic modifications. The problem we seek to address is that of subject-driven generation. Given a small set of images of a subject, we want to generate more images of that same subject in different contexts, while capturing the details of the subject. Can we do this using a detailed text prompt? We find that while we can vary the context, it is very hard to capture specific subject details by solely guiding the model using the text prompt. Can we do this using something like conditioning on the clip embedding from a reference image? In this DALL-E 2 example, we show that some subject details are captured. We have a yellow alarm clock with a number 3 on the clock face, but some details are not. The large yellow number 3 on the right side of the clock face is not captured. Additionally, we are not able to vary the context. Using DreamBooth, we are able to tackle both obstacles and can generate new images of the subject in new contexts while preserving subject details with high fidelity. Next, we see an overview of the approach. As mentioned, the 3 key parts of our method are the use of a small dataset of unconstrained subject images, the use of the subject's class name, and the use of a rare unique identifier to denote the subject. We fine-tune the pre-trained text-to-image model using this small dataset with the sentence a V dog in this case, where V is the rare identifier. For this, we use the diffusion denoising loss. Another element is our proposed class-specific prior preservation loss. If a model is fine-tuned naively, then there will be language drift, a phenomenon where the model forgets the meaning of the word dog and attaches it to this specific dog. We want the model to be able to generate other dogs too. So we concurrently fine-tune the model with dog images generated by the frozen pre-trained diffusion model. In the end, language drift doesn't occur, and the model is able to generate both our specific dog and other dogs. Finally, some modern architectures are cascades of diffusion models. We find that fine-tuning the super resolution modules helps with capturing the details of the subject, especially the earlier super resolution modules. Our method coalesces into striking results for different applications. For example, we can achieve strong recontextualization where the subject is imagined in different contexts and locations that are unseen in the input images. For example, this backpack in Boston or in the Grand Canyon. DreamBooth also allows for novel artistic renditions of a subject in different styles, such as this dog in the style of Renoir or Vermeer. An interesting one, property modification. Here we show examples of hybrids between our subject dog and other species. Using DreamBooth, we can also accessorize a live subject, for example, dressing up our subject dog in different costumes. And we show that our method can even draw comic vignettes by creating the first comic with a consistent character generated by a diffusion model. And it is shown right here. One key question is how to evaluate DreamBooth with respect to subject fidelity. For example, this dog on the left and the dog on the further right here, they are the same dog, but with a different background and wearing different accessories. These other corgi puppies, this one here and this one here, are not the exact same dog, but the images can have semantic similarities, such as the same orange background. How do we come up with metrics that can focus on subject similarities? This is a hard and unsolved problem. To start to address this question, we released the largest dataset for the task of subject-driven generation. Our dataset has 30 subjects with 3 to 6 images per subject in different locations and with different variations such as pose, articulation, and lighting. It has 21 inanimate objects and 9 pets. We also provide a set of 25 prompts to guide generation. We evaluate our method using this dataset. The dataset can be found online using this URL. Here are a few examples of the dataset prompts that we provide. There are recontextualization prompts such as a V-class in the jungle, and other things such as accessorization, a V-class wearing a Santa hat, or also attribute modification, a red V-class. We compare our work to the concurrent work of textual inversion that tackles a similar problem by encoding concepts into text embeddings using few-shot optimization. Textual inversion has certain advantages. The size of a textual inversion embedding is small compared to a whole DreamBooth model. Nevertheless, since it doesn't modify the output domain of the model, it has a hard time capturing some fine-grained subject details, such as the head in this statue example. We conduct a large user study that shows that human subjects prefer DreamBooth over textual inversion for both subject fidelity and prompt fidelity. We believe that rigorous user studies are the golden standard for evaluation of this task. Going back to the topic of subject fidelity metrics, clip image, which is the cosine similarity between the clip embedding of two images, has some shortcomings. For example, here the synthetic sample on the right scores higher in clip similarity to the reference than a real sample of the same subject. Clip works at a conceptual level that sometimes does not capture subject detail very well. We propose to also use dino cosine similarity, which has some shortcomings of its own, but performs better overall than clip similarity. Here, the dino metric correctly assigns a higher score to the real sample instead of the synthetic sample. Our experiments show that DreamBooth on Imagen achieves the best results for both subject fidelity and prompt fidelity using clip text-to-image similarity. DreamBooth on Stable Diffusion is a close second place, outperforming textual inversion on Stable Diffusion. One of the more interesting things about DreamBooth is the fact that it allowed for new applications, which the community pursued with enthusiasm. For example, one can train a DreamBooth model with images of themselves, generating AI selfies with beautiful semantic and stylistic modifications. I really like this example here. Benjamin Scott Pye on Twitter first generated some DALL-E ugly cute plushies, and then trained a Stable Diffusion DreamBooth model on these generations. And then that gave him endless ugly cute plushie generation capabilities. DreamBooth can also be used to generate cool assets for video games. These are examples by Emmanuel during the very, very early days after DreamBooth was released. And finally, something that really intrigues me, Roop here fine-tuned Stable Diffusion 2.0 on realistic portrait images, digging into the strong prior of the model and allowing it to generate photorealistic images of people early on after DreamBooth was released and before many other models could get images of this quality. So overall, we are really surprised and humbled by the creativity of the community to generate incredibly interesting things with such speed. Thank you very much for viewing this presentation and hope to see you at CVPR.